Alright, everybody. So we are going to start a new unit today. So, a couple announcements. First, I'm about halfway through the tests, grading of the tests. Two, starting April 13th is when the district is changing how things are going to work around somewhat. So, math lessons will be on Mondays and Wednesdays. Hopefully, I'm still going to get that 10 o'clock slot like we've been doing in the past. That way, it's still the norm. Fridays are teacher work days now, where I can communicate with your parents if I need to, but hopefully we've all been doing what we've needed to be doing in this class, so I'm totally happy with how it's been going. Tuesdays and Thursdays are going to be kind of like you have other classes. I don't remember what are the categories of those other classes, but you have them. But it's also going to be tutorial days so like recitation days for me, so that way you can ask questions. But honestly, if you have questions, keep asking them through the Remind. I may have to change the time slot of the recitations starting after spring break, because I think they want it to be somewhere between 9 to 2, but I know a lot of you either are working or your parents are working and you have to take care of your siblings, so I know that's going to be hard. So we're kind of communicate to one another through Remind or set up another survey to kind of see how that's going to work. But let's get into today. So this unit is on probability. So we're going to start by talking about combinatorics, which is actually a huge field in mathematics. So we're going to start by talking about the discrete part of mathematics, which means basically we're looking at individual numbers instead of a continuous stream of numbers between like all the numbers between 2 and 3, which is an infinite amount of numbers. No, we're just going to be talking about the number 2 and the number 3, and so forth and so on. So we're going to be talking about counting today. So one of the things for counting is how we can rearrange distinguishable objects. So for instance, how many different ways can I rearrange the letters A, B, and C? So I want to try to figure out how many different ways I can rearrange these 3 different numbers or letters. So one way that we can visualize this is using a tree diagram. We'll talk more about tree diagrams later, but this is a good starting point. So first, I could say, hey, my first letter I'm going to choose is going to be A. Or I could say, nah, I think my first letter I want to choose is B, or nah, I want to choose C instead. So those are my options for the first 3 letters of however I'm going to rearrange it. So now looking at the A, I can either go and say my next letter is going to be B, or my next letter is going to be C. Same for this B. It can be the next letter would be A, or the next letter would be C. For C, it would be A, or it would be B after that. So then I only have one more option. So first it was A, then it was B, so it has to be C. First it was A, then it was C, so it has to be B. First A or B, then A, so it has to be C. This has to be A. This would have to be B, and this would have to be A. So as you can see, I have a total of 1, 2, 3, 4, 5, 6 different ways I can rearrange just those 3 letters. So this is kind of what we're going to be talking about today, ways we can rearrange things. It's actually used a lot in science to kind of figure out whether or not some kind of test that they did actually like worked, or if it was too far from the randomness of things. So I can talk about an example of that. So an example of that, so let's say that we have a salesperson and they are trying to sell their $2,000 copying machine. and you have the option of keeping your original one, or you could go with a different brand that's like twice as expensive as this salesperson's. So his job is to try to show you that his lower cost machine is actually better than yours, or the $4,000 machine, whatever it may be. And how he does that is he takes 60 of your employees. So you're looking at 60 people, and he asks them, hey, I'm going to give you a printed out copy of your own machine, a printed out copy of my machine, and a printed out copy of the expensive machine. And I want you to rearrange those to place them where they belong. So you're trying to see, okay, this one is ours, this one's the $2,000, this one is the $4,000 machine. So after he did that, all of a sudden no one was able to identify all three perfectly. Out of all 60 of those people, no one was able to spot a difference or be able to arrange them correctly. So he's basically saying, because of this, you need to be able to buy my machine because you can't tell the difference of the other ones. So that's kind of his sales pitch. So one thing you have to kind of start to look at is, does that make sense? Would it be that if people even randomly started choosing, would they be able to get it correct? Because if all three of these should look exactly the same, then there's a probability that someone or some amount of people accidentally put them in the right order. So we can actually see what that is. So kind of the same kind of thing, if we have 60 people and there were 3 different things and there's 6 ways of putting it together, that means that we have a probability of 1 out of 6 to randomly put it in the correct order. So 1 being the correct order and 6 being your total amount of options. So if we have 60 people, that means if I multiply 1/6 times 60, that means 10 people should have randomly, more likely, roughly around that, put it in the right order. So more likely something fishy was going on with this salesperson, where he may have made it so you couldn't put it in the right order no matter what, to try to help his sales pitch. Because again, don't trust salesmen. Just kidding. Salespeople who are watching this. Okay. Alright. So one of the nice things about this is that we don't want to make these tree diagrams over and over and over. We don't want to try to figure out, oh, there's only 6 ways of doing this. But if I started adding more letters to this, you can hopefully see that these branches are going to start getting further and further out, because we have more and more options now. So because of this, we don't want to make tree diagrams and then count all the branches at the end, because that would be a pain. So what we actually have is what's called the multiplication principle of counting. And that multiplication principle of counting just states that all you have to do So if we have 5 objects, it's going to be 5 times 4 times 3 times 2 times 1. So I can figure out how many different ways to rearrange all of these by counting, or by multiplying the 5 times 4 times 3 times 2 times 1. And you can kind of see that if you looked at the first time we had, so for the A, B, and C, the first line we had 3 options we could choose. Then we only had 2 options we could go between. Then we only had 1 option to go between. Same with over here. Now we would have 5 options, A, B, C, D. But after we've chosen 1, then we only have 4 options left. Then we only have 3 options left. Then 2 options, then 1 option. So this multiplication principle of counting is going to be important for us. So that tree diagram is kind of like a geometric visualization of how this works. So one thing you also need to know is that let's say that we have some kind of procedure. So that procedure has some amount of sequences that create that procedure. So if each sequence has its own amount of times that it could occur, so like the first sequence has 5 ways or 120 ways that it can occur, so forth and so on, and then the second sequence has another some amount of ways it can occur, so forth and so on. So let's say that procedure has S1, S2, S3, Sn, different sequences, and S1 has R amount of ways that it could happen. S2 has a different amount of ways it could happen. S3, so forth and so on, have its own ways of happening. So if you wanted to figure out the total ways that the procedure can happen, it's just going to be R1 times R2 times R3 times Rn, so forth and so on. Meaning that you just are going to multiply each one of the different ways together to see the total amount of ways possible. So again, we're going to use that multiplication principle of counting. So again, we are multiplying things together. So one of the best ways to kind of understand this whole sequence thing is through license plates. So we all have license plates. If you are driving, your parents have license plates. Anything has license plates on the back. So with Georgia license plates have 3 letters. So we have 3 different letters. So we have some kind of letters, followed by 4 numbers. So if we wanted to figure out how many total license plates the state of Georgia can actually produce, we can do this multiplication principle of counting, because the whole thing of a license plate is considered the procedure. This would be sequence 1, so this first spot is sequence 1, sequence 2, 3, 4, 5, 6, 7, so forth, and it has a certain amount of options that it could go. And this one has a certain amount of options. This one, this one, this one, this one, so forth and so on. So we can actually multiply all those different ways of each sequence happening to figure out the total amount. So the first option, or the first example of this would be if there were no restrictions, meaning the same letter can pop up multiple times, the same number can pop up multiple times, and we want to try to figure out what the total amount would be. So for example, on this first one, this first sequence of spot, there are 26 letters in the alphabet. So that means that there are 26 numbers that could be in that spot. Same for this next one. There are 26 different letters in the alphabet. Same for this next spot. So with our numbers, so this is a single digit number. And there are 10 single digits if you include 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 10 different numbers. So that means this would get multiplied by 10, 10, 10, 10. So we can multiply all these numbers together and figure out the total amount of license plates the state of Georgia can produce if they continue using this pattern only. So multiplying these numbers together, I got 175,760,000 license plates. And that's if that the you can use the same letter and use the same number over and over and over again. So we can also look at this if there was a restriction saying that, hey, you can only use a letter one time and you can only use a number one time. You can't use them over again. So we can look at that math as well. So this time I can't use the same numbers or the same letters over and over again. So the very first spot though, I have all 26 options because I can choose whatever letter I want. I have, as of right now, no restrictions. The next letter, though, I can't use that number or that letter I've already picked. So I have one less option. So this is now 25. And for this third spot, now I've used 2 letters. So I don't get to use 2 letters of that 26, so I have one less again. So this is times 24. So we can do that same thing with our numbers. So at the beginning, I can use all 10 numbers. Then I can use one less, then one less again, then one less again. So now I can multiply all these numbers together. And I get a lot less. I only have 78 million different options I can use. That's 100 million less options because I put those restrictions on the amount of things that could possibly happen. So this is an example of the multiplication property of counting, including that different sequences and ways of each one. So you're just multiplying the ways of each sequence together at the end to find the total procedure. So there's 26 letters in the alphabet, Kalia. I'm going to try to start doing questions at the end because they're going to start restricting me to 30 minutes. So go through everything. So type in your comments in the live stream. Then I will talk to you at the end about any of your questions. Just write questions as we're going and I can just go back to them. I'm sorry. They're restricting my time limit that I can teach you. So, all right. So we're going to start talking about permutations. So with permutations are if the order that you are counting in matters. So the order things are getting placed in matters. So if we have an order that matters, so let's say that you're running a race, it matters who came in first, who came in second, who came in third, so forth and so on. So that order matters. So the nice thing about permutations is that the amount of objects you have, so n is the amount of objects I have, it's just going to be n factorial. So n being the objects. And the exclamation point means factorial in math. If you haven't done anything with factorials before, hopefully you have. But what this is basically saying, so 5 factorial is just 5 times 4 times 3 times 2 times 1. And if you notice, that was what we were doing earlier when we were counting the different ways that we were putting the letters A, B, and C because the order mattered for A, B, and C. So it's simply going to be a however many objects factorial. So all your calculators have the exclamation point. So mine is right here. So I just have to tap it and I can hit enter and I get 120 out. If you have issues with your calculator or you can't find the exclamation point, just send me a picture of your calculator that you have and I can try to tell you where it is. But so for permutations, if the order matters, it's simply going to be the amount of objects times factorial. So one thing that is actually interesting is that let's say that we actually have the same object in our list. So instead of me saying, hey, I want to do A, B, C, A, B now, and I want to figure out how many ways I can rearrange those, now I have the same object in 2 different locations. So I don't care that which A is in which spot. It's the same sequence. because they are the exact same object. So we have a different kind of formula if we want to place things in order, and we have the same type of object multiple times. So that formula is still going to be the amount of objects factorial, but now we're going to divide out the repeats, because there's going to be a sequence like this, but also a sequence like this. So this is a repeat of one another, where this was the first one, this was the second one, now it's the second and the first, but I don't care about that because they're both still the letter A. So I need to be able to divide out when this kind of stuff is happening. So what we do on that is we take that same object and divide it by the factorial. So basically we're just going to be multiplying and getting rid of all of the different repeats. So each time I'm doing a factorial, because there's multiple ways I can rearrange those same kind of letters. So if I had added another A at the end over here, that means that I now can do this same thing 3 times. Or actually more than that, I can do it 6 times. Because I can rearrange these 3 A's 6 different ways to be in the same locations. I need to get rid of that. So I'm dividing it out because this is going to happen multiple times when the other letters are rearranging. So, for instance, N1 would be the letter A, N2 would be the letter B, N3 would be the letter C, but I already counted the A's, so A was N1, B, so forth and so on. So, an example of this. So, I think we only got time for one example of this. So we're going to talk about the word bumblebee. And I want to figure out all the different ways I can rearrange the word bumblebee. Alright. So, I can count up to see how many different objects total I have. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 total objects. So the total ways I can rearrange this would be 9 factorial. But the thing is, I have repeats of certain letters. So I have B, and B happens 1, 2, 3 times. U happens only 1 time. M happens only 1 time. We already counted the B, so L happens only 1 time. E happens 3 times. So I don't really care about things that happen once, because 1 factorial equals 1 and anything divided by 1 doesn't really matter. So I'm only going to use these 3's right here. So I'm going to divide this number by 3 times factorial and multiply that by 3 factorial again. So I'm getting rid of all the times the B's are in the same place again, and I'm getting rid of all the times that E's are in the same place again. And I'm multiplying them again because of that multiplication property of counting. So I want to count all the times that all of these occur even at the same time. So we can then put this into our calculator carefully. Remember, put things in parentheses for your denominator. Do it for your numerator if you need to. So doing this, I get 10,080 ways that I can rearrange the letters in Bumblebee to where they're all unique. So I don't have the E's constantly in the same spot. I don't have the B's constantly in the same spot. So again, I counted the total amount of letters, which was 9. Then I had to divide out all my repeats. So B happened multiple times, E happened multiple times. So they each get their own factorial, and we multiply those together. So this is if you have the same thing and you're trying to distinguish between those same kinds of things. All right. So the more popular, or one of the bigger things is in counting problems, is if we have some amount of objects, but we only want to take out, say, of these 9, I only want to look at all the ways I can rearrange 5 of those 9. So this this is called permutations of n objects taken r at a time. So you will see this written as n big P r. So we have n amount of objects and I'm only choosing r of them. So let's say that I had 9 objects and I only wanted to look at 5 of them. So I want to see how many times I can use all 9 of these but only look at 5 of them. So that's kind of saying, hey, we have thousands of racers running this race and I only want to figure out the top 3. So how many different ways can I rearrange the top 3? I don't care about the positions after that. I only want to look at the top 3. But I can use every single one of those thousands of racers and put them in that 1, 2, and 3 spot. So I'm still going to get huge amounts of numbers. So this formula is simply going to be n factorial over parentheses n minus r factorial. Okay, so to kind of explain this, so let's go back to this bumblebee. So if I was using the bumblebee and I say, hey, I want to do, so I have n objects, or 9 objects. I want to figure out how many spots I can fit with 5 of them. So we could put this into our formula, and I'll explain why this makes sense in a second. So this would be 9 factorial over 9 minus 5 factorial. So looking at this, we can go and start simplifying some things. So this would get simplified down to n factorial over 4 factorial. So what I'm going to do now is something that you don't have to do, but I'm going to go and I'm going to actually split up the factorial to see what the multiplication actually looks like for each of these. So this would be 9 times 8 times 7 times 6, 5, 4, 3, 2, and 1. And the 4 factorial is 4 times 3 times 2 times 1. So notice how the 4, the 3, the 2, and the 1 are all going to cancel out. And if we kind of look back at that license plate problem, so if I had 5 different things, the first I have 9 different options to choose from. Then I only have 8 options, then 7, then 6, then 5. Notice that's what this is right here. 9 times 8 times 7 times 6 times 5. So I'm still filling those spots, but each time I'm getting rid of the one I just used. So this is choosing, so this is your permutations of n objects taken r at a time. So a couple nice things about this, you don't have to always put things into this formula because your calculator has this button. It has the permutation button. So you would go and type in 9, then you would look for the NPR button, and then you would type in 5, and this would give you out 9 times 8 times 7 times 6 times 5. So this NPR button is typically hidden under like a probability button somewhere on your calculator. Mine is at the same location as my factorial button, so I just have to click through it a couple times to get to the NPR. So again, if you have trouble with your calculator, send me a picture of your calculator and I can try to help you with that. But we need to still move on for now. So we did one example of this, so if I had put this into my calculator, this gives me out 15,120 different options or ways we can use the letters bumblebee but only take 5 of them. So using all 9 of those but only rearranging them using 5. A couple things. So again, just find this button in your calculator and it will make things go a lot quicker. So another example of this, let's say, so this is probably more relevant to some of you. Let's say that there are 16 actors going for an audition to be the 7 dwarves for Snow White. And we want to see how many different ways of those 16 people can be chosen for those 7 spots. So because the order matters here, because you can be sleepy or you can be dopey or so forth and so on, you have an order to who gets to be what. So it's not that, hey, I got a job, it's you became this spot. So the order actually matters. So this is a permutation thing. So we have 16 people going for 7 spots. So this is going to be the 16P7. So given 16 objects, choose or take 7 of them. So we can put this into the formula if we wanted to. So this would be 16 factorial over 16 minus 7 factorial. And we can put this into our calculator, either putting it into the formula as you see it, or using that NPR button. So, there are 57 million different ways that we can take 16 people and cast them for just 7 spots. That's a lot of different ways you can cast 16 people for 7 spots. But it's true. Because you have to imagine all of the different possibilities that could happen. So, that is going to be it for the day. So I'm going to look at the questions real quick, answer any questions. Otherwise, your homework is on the website. Also, don't do anything over spring break for my class. Relax, do things with your family, whatever. Just don't do any work over spring break at all for my class. Enjoy it. I know a lot of you still have to do work or still have to take care of your siblings, but do that instead of any kind of work. Don't stress out. Play some video games, whatever. TikToks, make them. Learn those dances, whatever. Brandy didn't get what answer? Alright, if there are no other questions, enjoy your break. I'll be on again at 5 today, just if you have any questions over this kind of homework on Zoom. So I'll put an announcement out later. But enjoy your break.